I'm Prajval Kumar Murali. I'm a PhD candidate at the BMW Group and the University of Glasgow. And on behalf of my co-authors, I'm very excited to present our work on towards robust 3D object recognition with dense-to-sparse deep domain adaptation. In our everyday lives, we do many tasks wherein tactile sensing is involved. For example, we can, with just the sense of touch, we are able to distinguish objects in our pockets, for example, a key or a coin. Similarly, we can distinguish various objects in a bag wherein there's limited visual perception. And for some of us, wherein we have imperfect vision, we can when we have to search for glasses, we can use we typically use our hands to try to find out where our glasses is in the space around us. In all these cases, typically what we are doing is we're trying to leverage the knowledge that we have gained from visual perception to use tactile perception to identify such objects. This is known as vision to tactile cross-modal transfer, wherein visually we can recognize an object as a key or a coin. And then if vision is not present in certain situations, then we can use a sense of touch to classify or to identify different objects. Cross-modal perception, vision to tactile cross-modal perception has been studied quite intensely in neuroscience from newborn infants to adults. And it's also been shown in other animals and in non-vertebrates such as insects as well. In the figure shown here, just to check if my cursor is being seen.
Yes.
Okay. In the figure shown here, you can see the different kinds of properties that are seen by each modality. So the visual modality can recognize color, brightness, unfamiliar shapes, and 3D geometry and orientation and so on. Whereas through the sense of touch, we can recognize mass, hardness, temperatures, fine textures, approximate textures, as well as familiar shapes. So what we are interested in is, can we try to give artificial agents this ability of vision to tactile cross-modal transfer, wherein we are mainly looking at shape. If shape can be transferred from one modality to another modality. Consider the situation shown here, wherein we have two robots. One robot is equipped with vision sensor, and another robot is equipped with a tactile sensor. Typically, a robot equipped with vision sensing can learn about different objects and learn to classify the various objects in the space around it by capturing images, labeling, and training a neural network. What we want to see is, can we leverage this knowledge that is gained in order to do tactile-based classification, as you see here, with the other robot having a tactile sensor on it, to do tactile-based classification without explicitly training a tactile network. What I want to do is, what I want to say is that we don't want to explicitly collect and label new tactile data and train a network, but actually leverage a prior known knowledge from vision to do vision to tactile cross-modal transfer. What is the advantage? The advantage is that we can leverage easily available dense visual data for tactile-based classification, wherein tactile data is very difficult to, of course, very difficult to acquire because of you need to perform actions, it needs to be in contact with an object and so on. And there's no explicit training with tactile data. This also gives minimal overhead for data collection and annotation. And it also increases the robustness for artificial agents such as robotic systems, wherein it can switch between different modalities without explicit training in each modality. For instance, if in cases wherein the camera is not working or the camera is occluded, a robotic system can switch to the tactile modality to complete the task of object recognition without spending time on data collection, annotation, and training, and so on. Now that the motivation is more or less clear on why this is important, why is this an important problem to solve for artificial agents, there are some challenges which come up. In typical array-based tactile sensors that are commercially available and which can be used for robotic grippers, as shown here, we can acquire tactile data by performing contact locations, by touching the object from different locations. This kind of actions gives us very sparse data, very sparse point cloud data. These point clouds represents the 3D location of the objects itself. And these data are in the range of about 50 to 100 points. Whereas typical cameras provide us very dense data. The dense visual data is around 50,000 to 100,000 points. So there's now a domain shift. There's a gap between the kind of data which we get from tactile sensing and the kind of data that we get from visual sensing. Of course, we are putting them both into the point cloud data structure because we are interested in the shape of the object. So each point represents a 3D point in space, and this gives us the shape of the object. Such sparse, dense data sets can also be acquired for other applications such as autonomous driving, because in autonomous driving, if you have a LiDAR sensor, it gives very sparse data. And also with stereo vision, you can get very dense data. So these kind of dense and sparse modalities are not just specific to tactile and vision sensing, but also for other domains as well. What we want to do is we want to do something called domain adaptation. So what the objective is that we train a neural network with dense point clouds. These are dense and labeled point clouds. And then we want to use the same neural network with sparse point cloud, typically from tactile sensing, and to do classification. There is without any changes, without very minimal changes, I would say, without actually explicitly training with tactile data. The dense data set is called the source domain, and the sparse data set is called the target domain. Typically, if you train a neural network or a classifier only with data that you get from a source domain and try to use the same thing on a target domain or a different domain, such a classifier would result in multiple misclassifications. As you see here, this is a simple infographic which shows that there's misclassifications involved if the classifier that you use, which is only trained on one set of data and has not seen anything from another distribution, it usually results in misclassifications. This is due to the domain shift or the change in distribution from a source domain to a target domain. What domain adaptation does is basically tries to bring these two domains together or bring them closer together. And we can adapt this classifier so that it works well both for the source domain and for the target domain. So the key idea is that we can use a small subset of unlabeled target data. So we're not spending human annotation time for labeling target data, but a small subset of target domain data in order to perform domain adaptation. So the first step, what we do is we're doing classical training. So we have a neural network design here. We have dense point cloud data and the associated labels as well. This is classical supervised learning. Our neural network architecture is based has a backbone of PointNet architecture because PointNet has been used very well for point cloud data for neural networks. So it can take in raw input point clouds. It gives us a global feature vector above 1024 values, and then we have 3 fully connected layers, which is then used for classification. We use cross entropy loss in order to train this neural network. For the domain adaptation step, what we do is we take a smaller subset of unlabeled sparse data, and then we freeze the feature extraction layers because the feature extraction layers itself are very general. They given a point cloud data, they provide a feature vector, whereas the fully connected layers are actually used for a specific task. So it goes from the left to right, it goes from very general to very specific. So we are basically freezing certain bunch of layers, and we're training only the specific layers, and we're using a 2-stream layer training, as shown in the right side figure here. Because we're using unlabeled data, we don't have labels. We don't have labels to actually try to supervise train on the target data set. So we devised a novel domain adaptation loss function, which I will now talk about. One more thing that we have to see here is that we're using multiple layers, the layer 1 and the layer 2 here, in order to do domain adaptation, because we see that this provides a much better generalization from a source domain to a target domain. For domain adaptation itself, we use 2 methodologies. The first one is known as maximum mean discrepancy, which has been used which has been proposed for domain adaptation. What it basically does is that it takes the source domain and target domain distributions and maps it into a reproducing kernel Hilbert space, a different space, and then it tries to minimize the distance between the means of the two distributions. This tries to bring the source domain, the mean of the source domain, and the mean of the target domain closer together, which then can make a classifier which works well for the source domain, also work well for the target domain. But this will not give us sufficiently good results on its own. So we also use another metric called the correlation alignment. The choral loss, instead, the MMD loss works on the means, whereas the choral loss works on the covariances or the second order statistics. As shown here, choral loss proposed previously uses the distributions, the source domain and the target domain distributions. The covariance or the second order metrics of the distributions are used to minimize, and then they're brought closer together. By combining these two, we can have a normal loss function wherein we use the cross entropy loss for supervised training whenever labels are present, and then the MMD and the choral, which is used in linear combination together with some weighting factors alpha, beta, and lambda. So this loss function that we propose can be used for actually performing domain adaptation, wherein the two distributions, the statistics of the two distributions from the source or the dense domain and the sparse domain can be brought together. We ran experiments first in simulation. So we use the ModelNet 10 dataset. The ModelNet 10 dataset consists of about 5,000 different CAD models of different objects, which basically are in 10 classes of objects. We then sampled a dense point cloud data from these objects and then a sparse point cloud data. So dense point cloud data consists of about 1,024 points, whereas the sparse point cloud ranges between 10 to 50 points. What we want to do is basically train on the source domain and use a subset of the target domain, unlabeled subset of target domain to do domain adaptation, and then try to see how it works on very sparse points. We ran experiments shown here this is the test accuracy shown here. We also tested against state-of-the-art networks. So we wanted to see how state-of-the-art networks performed on very sparse data. As you may expect, on dense data sets with 1024 points, most of the networks here perform really well. They perform with very high accuracies. But whereas when you go to very sparse points from 10 to 50, the performance reduced massively. Our model here shows quite good performance, even about 80% for 50 points, and about 75% for about 30 points for even very low point numbers as well. So this shows that the state-of-the-art networks are not robust to points, to the number of points, and as the number of points reduces, their accuracy falls massively. So the robustness, we cannot directly use such networks. So, and this is where it shows that domain adaptation actually helps to pump up the accuracy even for very sparse point clouds that you typically get from tactile sensing or from vision and tactile sensing. We also used different experiments wherein we tuned our alpha, beta, and lambda parameters as shown here, where we tried different values, and we did for tuning of these hyperparameters. And so what we show in this contribution is that we show a novel transfer learning method for dense to sparse domain adaptation. We show that our network also outperforms other neural networks for sparse point clouds, which is typically you can get from tactile sensing. What we show is that we can increase the robustness for robotic systems, which can then use which can choose which kind of modality to use depending on if a modality is available or not. So if vision is not available, it can use tactile sensing in order to perform classification, wherein we don't have to explicitly train the tactile modality. Of course, we recognize that cross modality or vision to tactile cross modal is a very big aspect, wherein we are just looking at the shape or the 3D locations of shape. We can also try to extend this work into other contact-rich information such as texture, temperature, and so on, wherein we can, as humans, we are able to just identify with temperature by looking, and then by touching, we can identify different kinds of properties of objects, but not just the shape of the objects. And that's brings the end to my talk. Thank you very much. I'm looking forward to any questions.